Electrical engineers think reducing the speed of a pump will save energy. Mechanical engineers think restricting the flow will make a pump work harder. Neither of these things is true.
Hello, all of you beautiful people. This is Michael Martin from Ultimate Pool Guy and MPS Pools, and welcome to my variable speed pump video that will likely turn into a series. So, I am a 16-year career pool professional. I both service, maintain, and build swimming pools. Variable speed pool pumps have been available in the open market now for decades. Variable speed pool pumps have risen in popularity in the pool industry in the last several years, being pushed by all the major manufacturers as well as utility companies. They're claiming massive cost savings, reduction in energy usage, all for a reduced price. They're offering massive rebates, $1,000 and more, in order to push this product on consumers and see more and more of this out in the field. What I have seen is a rash of green pools, unhealthy looking water, all as a result of variable speed pool pumps running at a lower RPM, which equals reduced circulation and water filtration. I have been of the opinion now for a long time that variable speed pool pumps are not the correct application for a pool circulation pump. I personally run my variable speed pool pumps out in the field just like a single speed pump. That means I dial it all the way up to full speed, 3,450 RPM, and I will typically run it for a full run cycle, 6 to 8 hours per day while the sun is shining on the water. Now, what they are trying to get us to believe is that by operating a pump at a lower speed for a considerably longer period of time, that is now translating into the same filtration and water turnover, however, at a reduced cost and energy consumption. Now, to many of my contractor friends and some electrical engineer friends of mine, this all sounds very fishy. These variable speed pool pumps are outfitted with a huge motor. They're outfitted with a 3 horsepower motor. So a 3 horsepower motor being run at a lower speed over an extended period of time, in my head, translates to the same or more energy consumption. Now, you take this back to the manufacturers and the utility companies, and you can see why they might be really pushing this product on us, telling us that it's saving money. Why? Because it's selling more product for the pool manufacturers, and it's selling more energy for the utility companies.
There's $27 billion worth of variable speed drives sold every year.
For example, if they wanted this to truly be an energy saver, why did they not build these pumps with a 1 horse motor or a 3/4 horse motor?
Yeah, that was exactly what they did with the pool industry. They outfitted these variable speed pumps with the highest available horsepower motor, a 3 horsepower motor. And if they were interested in the electrical savings, why didn't they not outfit them with a 1 horse or 1.5 horse?
Yes, sir. Yes, sir.
They went straight to the 3 horsepower because that's going to gobble up the maximum amount of electricity.
Well, not so much that, but you have to oversize a pump with a VFD because of the affinity law. The second part of the affinity law says you lose head by the square of the speed. So a flat curve, centrifugal, single impeller pump like a pool pump, you can't slow it down but about 5%, or you don't have the 30 pounds of pressure you need for the filter to work anymore. So they start out with a 3 horse pump that will build 60 pounds of pressure, so they can slow it down about 20% and still have the 30 pounds of pressure you need. But if you start out with anywhere close to the right, you're exactly right. If you start out with anywhere close to the right size pump, you can't slow it down or it won't do what it's supposed to do because it's running at its best efficiency point, giving you the most gallons per kilowatt that you can possibly get because you're not restricting it or slowing it down.
So they put the 3 horsepower motor on it to compensate for the lack of design or to compensate for the weaknesses.
To compensate for that affinity law.
Wow.
Because you can't slow it down enough to save any energy if the pump was anywhere close to the right size to start with.
So, all of these arguments are going to be brought up in this video as well as all subsequent videos. In my research for these videos in this project, I had spoke to a lot of my electrical contractors, electrical engineers, and then I came across Kerry Austin. Kerry Austin runs an outfit called Cycle Stop Valves out of Texas. Now, he deals with pumps in relationship to well water. Now, I know the argument that I'm going to get is, hey, Mike, this is not an apples to apples comparison. You're giving us information that is coming from a guy that studied these and deals with well water. However, the engineering, the math, and the science behind it all is all exactly the same. So Kerry provided me a wealth of information. You should check out his YouTube channel, Cycle Stop Valves. I will include a link in the description below. I'm going to candidly share with you our phone calls, his videos, as well as the cumulative information that I've been able to put together on this topic. And you decide, are we getting the truth? Are we being lied to? Is this simply a misunderstanding or a lack of knowledge in how to read a flow chart? Let's jump in. You decide.
The curved vane centrifugal pump, most commonly used today, was invented in 1851. Nothing uses less energy than a normal centrifugal pump running at full speed and operating at its best efficiency point. Many people have tried, but no one has been able to improve upon this centuries-old design.
So nothing uses less energy than a single speed pump at its best efficiency point. So to understand a single speed pump and its best efficiency point, we also must understand how to read a flow chart.
When a pump is built, it is put into a test pit and run through its paces. The performance of the pump is plotted from 0 to max flow rate. Connecting the dots produces a pump curve. Guesswork, fuzzy math, and personal opinions don't apply. The pump curve shows you exactly what the pump will do. Manufacturers can supply a certified test, and you can even witness the test on video.
Guesswork, fuzzy math, and personal opinions do not apply. So this is what we call a hard science. A soft science is something that changes, like the weather. The weather is a soft science, okay? What Kerry Austin is presenting to us, this is a hard science. This cannot be argued. He's going to prove to us that variable speed pumps are a hoax, actually costing us more money over the lifetime of the pump.
Pump curves can show the horsepower, the efficiency, and the net positive suction head required. It can also have multiple performance curves depicting different impeller diameters and/or multiple pump speeds. Don't let any of this confuse you. Most pump companies' electronic catalog will let you X out the parts you don't need to see. In most cases, we only need to look at the performance and horsepower curve for a single speed pump with a set impeller diameter. Lift in feet of head is on the left side of the performance curve. The flow rate in gallons per minute is on the bottom of the performance curve. The horsepower curve shows how much energy is used at all different operating points. Notice how the horsepower goes down as the lift or pressure goes up. It is completely counterintuitive, but restricting the flow of a pump reduces the horsepower or energy used and makes the pump work easier, not harder. As you can see, the horsepower for this pump naturally drops by 50%, from 24 horsepower at 300 gallons per minute to just 12 horsepower at 10 gallons per minute, without varying the speed of the pump.
Okay, this is very important. The horsepower organically reduces as the pressure on the pump increases, which means the electrical draw on the amps automatically reduces as the back pressure on the pump increases.
To a pump, 1 pound of pressure is the same as 2.31 feet of lift. So to get 50 psi at the faucets, the pump must produce 50 times 2.31 or 115 feet of lift. That 115 feet of lift for the pressure must be added to the actual pumping depth to water in the well. If the pumping water level in the well is 100 feet and there is 5 feet of friction losses in the pipe, the pump must be able to produce 15 gallons per minute from 100 foot depth, plus 115 feet, which is the 50 pounds pressure needed, plus 5 foot of friction loss, for a total dynamic head of 220 feet. We look for a pump with a performance curve that intersects at 220 feet of head and 15 gallons per minute. This regular submersible pump, which spins at a constant 3450 RPM, fits the requirements.
So what Kerry's explaining here is he has not actually messed with the running speed of the pump. The pump is still spinning at a 3,450 RPM. However, he's demonstrating that by increasing the pressure on the pump, it is drawing less electricity. It's having to work less.
With this electronic curve, selecting the operating point of 220 feet and 15 gallons a minute will put a corresponding point on the horsepower curve. You can see this pump will use 1.392 horsepower at 15 gallon per minute flow. Putting another operating point at 2 gallon per minute flow shows the horsepower required decreases from 1.392 at 15 gallons per minute to 0.627 horsepower when the flow rate is restricted to 2 gallons per minute. That's right. The pump speed or RPM stays at the normal 3450 RPM while the energy consumption drops by 55% when simply restricting the flow with a valve.
Now, I know the argument everybody's going to write in with and tell me that, Mike, this is not a pool application. However, the science is still the same. Cary is still dealing with centrifugal pumps. He's still dealing with pumps that have a motor, an impeller, a diffuser, a seal plate, mechanical seal, all the same stuff that our pool pumps also deal with. He's just dealing with it in a larger scale because he's dealing with well water extraction in Texas.
Now let's look at a variable speed pump curve for the same application. Also known as variable speed drives, variable frequency drives, or just VFDs, the area shaded in blue is the supposed working area for this pump at varying speeds. Many engineers preach about the affinity law. They make a big deal about how horsepower is reduced by the cube of the speed, which shows a 50% reduction in speed will cause almost a 90% reduction in energy use. With this electronic pump curve, there are lines marked all the way down to 30% pump speed. If you place a point at 30% speed and 2 gallons per minute, it will show the horsepower will drop all the way down to 0.049 of a horsepower. That's impressive, right? However, the most important part of the affinity law, which many engineers conveniently try to forget, is that head or pressure is lost by the square of the speed. At 31% speed, this pump can't even lift water out of the well, much less build the 50 pounds of pressure needed.
So that actually doesn't matter if you have a 3-horse pump, a 20-horse pump. It doesn't matter if you're asking the pump to move 2 gallons a minute. In this case, it's using 0.049 horsepower. This is fascinating what he's about to tell us right here. This is where the variable speed pump savings idea, that argument, falls completely apart in my opinion.
The pumping level of the well will always be at 100 feet, and the system will always need 50 psi. So the pump must always deliver at least 220 feet of total head. The most this pump can be slowed down and still produce the 220 feet of head needed is only 20%, not 70% as many falsely believe. Anything lower than 80% of full speed will not lift water out of the well or produce pressure to the faucets. And since 80% of full speed is the slowest speed possible, reducing energy consumption by the cube of the speed doesn't add up to much.
So our translation for swimming pools, he's comparing it to his well water usage, is we need circulation. We need XYZ gallons of turnover per day multiplied by XYZ gallons a minute, and this is going to produce XYZ healthy looking pool or not healthy looking pool.
As you can see, placing a point at 220 feet ahead and 2 gallon per minute flow shows the pump can only be slowed by 20%. This requires 0.583 of a horsepower, which is 92% more energy than the 0.049 horsepower many would like for you to believe.
There it is, folks. Very fascinating. So to do the same work, to move the same 2 gallons that he is using in this example, a pump that is running at a slower speed. So to do the same work, the same 2 gallons of work, the variable speed pump is working 92% harder. And that's just this example. My phone call with Cary later in that day, his opinion is that variable speed pumps are costing between 500% and 700% more over the lifetime use of the pump.
I saw in your video, it went up, in your example in the video, it went up almost 300%.
Yeah, and that's a low case. Most of them 500, 700%. Depending on the actual pump.
The pump must always maintain 220 feet of head, so none of the shaded area below the red line is usable. Since 0.583 horsepower is the least energy use possible with a variable speed pump, there is only a 7% difference in the 0.627 horsepower needed by simply restricting a normal full speed pump with a cycle stop valve or CSV. Then, when you look at the power needed for the maximum flow rate of 15 gallons per minute, the variable speed pump uses 1.515 horsepower, compared to a normal full-speed pump using only 1.392 horsepower. In spite of these facts, many people will see the amp meter dropping from 1.515 horsepower at high flow and high RPM to 0.583 at low flow and low RPM and still say, "Look, the VFD is saving 62% in energy." But wait a minute, not so fast. Decreasing the speed only reduces the horsepower needed to spin the pump and motor. Varying the speed actually increases the energy consumption per gallon produced.
So what he's saying is to do the same work to achieve the pressure that he needs for his well water clients, or in our case, to achieve blue pool, healthy looking water, is a certain amount of work. And to achieve that work, so for him, provide 50 psi of faucet pressure to his clients, and for us in the pool industry to achieve blue, healthy looking pool, we are actually paying more to arrive to that using a variable speed pump over a single speed pump.
Looking again at the maximum flow, producing 15 gallons per minute with 1.515 horsepower is using 0.101 horsepower per gallon per minute produced. This pump, slowed down by 20%, is still using 0.583 horsepower for only 2 gallon per minute flow, which is 0.292 horsepower per gallon per minute produced. That is a 290% increase in energy use at low flow caused by varying the speed with a VFD.
So if you all kind of followed along with that the slower a variable speed pump is working, the less efficient it's becoming, and to do the same amount of work, it's going to now require more runtime and more energy to arrive at the same place as a single speed pump that was running at full speed when appropriately sized for the application.
Then if you compare a normal full-speed pump producing 15 gallons per minute at 1.392 horsepower to the variable speed pump at 1.515 horsepower, the variable speed pump is using 6% more power per gallon produced at high flow rates.
So even at high flow rate, even at max flow, the variable speed pump is still consuming more and still less efficient. Shocking.
Even with state-of-the-art technology, permanent magnet motors and all that, variable speed pumps always use more energy per gallon, not less. Variable speed pumps always use more energy per gallon, not less. Variable speed pumps always use more energy per gallon, not less. Why are so many manufacturers, engineers, utilities, and government agencies still promoting VFDs as energy savers? Pump and VFD manufacturers are raking in the profits by letting everyone believe these misconceptions.
There's $27 billion worth of variable speed drives sold every year.
Ultimately, it is costing consumers and taxpayers way too much. Submersible, turbine, centrifugal, jets, and even pool pumps work the same way. A VFD is just trying to trick a pump into doing something it already does naturally. Learning how to read a pump curve can help save energy, reduce cost, and make your pump system last longer. There is no need for third-party verification, studies by the government, or an accredited university. When you know how to read them, everything can be verified by the pump curve.